In masked language modeling, input sentences are corrupted by masking and replacing words, and the model is tasked with reconstructing the original sentence. In warped language modeling, input sentences are additionally corrupted by randomly inserting or deleting words, and the model must predict which words were deleted by the corruption and which words did not belong in the sentence. However, warped language models are not able to reconstruct the original sentence because they are not able to distinguish between the deletion and substitution operations. Sentence representations learned by warped language models are intended to be robust to the loose grammar of human speakers and to the kinds of errors made by transcribers. Meanwhile, accurate ground truth labels are required for state-of-the-art speech recognition systems. Since the strengths of a human and a machine transcriber rarely coincide, a cooperative approach between a human and a machine could be beneficial for creating labeled datasets. In this work, our goal was to create ASR data labels that accurately reflected the ground truth speech by either improving the accuracy of human transcriptions or by improving the accuracy of an ASR model's hypothesis, both as post-processing operations. To this end, we made a simple modification to the warped language model architecture. In addition to predicting a token at each time step, we predicted how this token must be used to reconstruct the original input sentence. In particular, this extra information allowed us to differentiate between the substitution and deletion operations, as we previously would not have known which of the two operations to perform when the encoder predicted a token that was different than the input token. Now that the WLM was capable of correcting errors in written text, we pre-trained the model on English Wikipedia. We adapted the pre-trained model to transcriptions of Alexa data in the following supervised fashion. We viewed an individual transcription of an audio file as a corrupted version of the ground truth speech, and we allowed the warped language model to predict a consensus transcription of the same audio file, which we refer to as the gold transcription. To enable this, we first had to compute a viable sequence of operations that would transform the gold transcription into the input transcription. There was not always a unique such sequence, but we were guaranteed to be able to find at least one. The idea was that during inference, the model would be able to produce a high-quality transcription from any individual data label, be it from a human or a machine. This idea didn't work very well due to hallucination, but our next idea was to feed in multiple hypotheses at the same time in order to produce a gold-quality transcription. This method worked very well when we combined a human transcription with an ASR model's 5 best hypotheses. We used a position sharing system in which the first token of the first transcription had the same position embedding as the first token of the second transcription and the third, and so on. After fine-tuning the model on 400,000 pairs of one-pass and consensus transcriptions, we found on test data that the resulting corrected transcriptions had a 10% lower word error rate against gold than the input transcriptions.